This section, we're going to talk about conditional probability. What is the probability that something happens given some information you know about the situation? What is the probability? So F and G are events. What is the probability that F happens given that G has already occurred? Well, the first comment I'll make is if G has occurred, if event G has happened, that means the probability of G has to be bigger than 0. Usually it's between 0 and 1, and it could include 0, it includes 0, and it includes 1. But it can't be 0 in this case, otherwise it didn't happen. But we're assuming that G has happened. So it's bigger than 0. Now, what does this mean? So you have the sample space, and you have event F, and you have event G. Now, it might very well be that F and G do not intersect. Now, what is the probability that F occurs given that you're in G? Well, we're in G. That's what I call our reduced sample space. What comes after the vertical line is the description of the reduced sample space. So the denominator, number of elements, and the denominator goes in the bottom. We can call that the probability of G. Now, we want F to happen. Well, if you're in G, if G has happened, the only way F can happen is if you're here in the red. But that area is the probability of F. Now, if I wanted to be more formal, I would not have written down that first. I would have written the number of elements in F intersect G, that's the probability you're in the red, divided by the size of the sample space, the number of elements in G. But if I divide each of these by the same number, it won't change the value. I'm going to divide by the number of total elements in the universe, divided by the number of total elements. Now, this numerator, that numerator, why, you know what? That's the probability of F and G. And the denominator, this denominator right here, that's the probability of G. So, see, the formula is exactly what I have on top. Now, if it turned out that we are in this scenario, that is F and G don't intersect, well then the probability of F and G would be 0. And remember, we said the probability of G was positive, that is not 0. And 0 divided by not 0 is 0. If F and G can't happen together, the chances that F happens, given that G happened, is 0. The probability that you get a B in your probability class, given that you got an A in your probability class, is 0. You got an A, you didn't get a B. We can talk, well, a non-zero probability would be, what's the probability you got a piece of an A? Well, let me not say that. What's the probability that you got an A, given that you got a piece of an A? A piece of an A would be, well, some schools do give an A+, an A, or an A minus. These are pieces of an A. What's the probability that you got an A, given that you got a piece of an A? Okay, that would not be 0. So A nice problem would be, what is the probability, so you toss 2 dice. What is the conditional probability that at least one lands on a 6, given that the results are different? So you toss 2 dice. What is the probability that at least one die lands on a 6, given that their 2 dice are different, given different results, different tosses? Now, you can use the formula, but it's usually easier to just do standard probability using the reduced sample space. What comes after the line and before the closed bracket, that's the reduced sample space. Okay, let us look at this reduced sample space. Well, normally if you toss 2 dice, you will get one of these 36 results. You can get first a 2, and then a 1, a 2, a 3, a 4, a 5, and a 6 next. Or first you can get a 3, and then a 1, or a 3, and then a 2, etc. But let us do this correctly. Okay. You can get a 3 and a 3, and then a 3 and a 4, a 3 on the first, a 5 on the second, 3, 6. Same game with the 4. This is the standard, or this will be the standard sample space for throwing or tossing 2 dice. But we want to get different results. We want to get different results. We don't want to get 1 and then a 1. Those are the same results. We don't want to get a 2 and a 2, a 3 and a 3, a 4 and a 4, a 5 and a 5, a 6 and a 6. So in other words, there used to be 36 results in this table, but I just knocked out 6 of them. So there are 30 remaining. How many of them have at least 1 6? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 30, also known as 1/3. It's very clean to do it that way. That is, to deal with the reduced sample space as opposed to dealing with the formula. We get 1/3. Now, I'm going to be bold. I'm hoping I'm not going to be sorry, but I'm going to be bold and use the formula. Don't use the formula. It's harder. But if you can use the formula for the harder problems, the ones that really require the use of the formula, you'll be able to do it easily. So this is my F. All of this is my F, and this is my G. What is the probability of, well, what does it mean at least 1 is a 6 and different results? Well, probability that you get, now, if they're different results, you're not going to get double 6s. Okay, so this is the intersection of these two is exactly 1 6. Exactly 1 6. And we want to divide by the probability that you get different results. If you're going to get at least 1 6, that means 1 6 or 2 6s. You couldn't possibly toss 2 dice and get 3 6s or 4 6s or 11 6s. You get 1 or 2. Well, if you get exactly 1 6, then yeah, they were different. If you get exactly 2 6s, well, no, they weren't different. And for intersections, they both have to be true at the same time. Now, what's the probability you get exactly 1/6 when you toss 2 dice? Well, there are 36 outcomes, and exactly 10 of them have 1/6. You can have a 1 and a 6, and a 2 and a 6, a 3 and a 6, a 4 and a 6, a 5 and a 6, a 6 and a 6. You can have a 6 and a 1, a 6 and a 2, a 6 and a 3, a 6 and a 4, 6 and a 5, and I've already said a 6 and a 6. But this one gets knocked out because it's not exactly 1/6. This has exactly 1/6. This has exactly 1/6. So does that. There's 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 of 36 times, you'll get exactly 1/6. Now, you want different results. Well, there are 36 results. How many of them are different? Well, of the 36, let's remove the ones that aren't different. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Those are 6. There are 36 results. 6 of them are not different. Exactly 6 of them are not different, leaving 30 left over. The remaining 30 are all different. Okay, now, if I multiply this number by 36, that cancels out. But if I multiply the top by 36, I have to do the same to the bottom. That cancels out. And what I get is 10 divided by 30, which is 1/3. So I got the same answer as before using the formula. But again, unless you can't do it otherwise, don't use a formula for this type of problem. I'm not saying that if you don't know how to do it the other way, but you can actually do it using the formula to leave the problem blank on an exam. No, use the formula. But I'm saying it's easier not to. Now, let's do an urn problem. We have this urn. It has, say, 8 white balls and 4 black balls. And you want to select 4. Select 4 balls, we'll say with replacement. With replacement. That is, you take the first ball, you put it back. You take the second ball, you put it back. In the end, you select 4 balls. Okay. What is the conditional probability that, say that the first and third balls are white, given that there are exactly 3 whites. Given that the sample contains exactly 3 whites. Okay. So you have 4 positions, the first, the second, the third, and the fourth. Well, we know what we want in the first and the third. Well, if there are going to be, if we are given that it contains exactly 3 whites, well, that means in position 4, we have a third white and, I guess, a black. Of course, it could be a black, then a white. Doesn't matter. All we know is we used a black. We are given that we used 1 black and 1 white ball, and now we want to know the probability that the first and third are black. the probability that the first equals the third equals white. The probability that the first and third position are white, given that we used one white and one black for positions 2 and 4. Okay, we've used a white and a black. That's what I take from, we're given that we've used or picked at exactly 3 whites. Okay, position 2 and 4, they used a black and a white. And this 2 just does not want to come out nice. All right, so what does that mean? That means there's 7 whites and there are 3 blacks. We want to know the probability, with replacement, that we will get 2 whites. We want to pick a white and a white. A white and then a white. Well, there are 10 balls in the urn. 7 of them are white. We pick a white, we put it back. There are still 10 balls in the urn. 7 of them are white. The answer is 49 out of 100. 49% of the times, if position 2 and 4 have a white and a black, 49% of the times, the first and the third will also be white. Well, the first and third will be white. Now, what if I say without replacement? Put a little O there, without replacement. Now, that one's going to change. We initially started with 8 whites and 3 blacks. We absolutely picked the white and we picked the black from that. There are 10 balls remaining. The first time we go in to pick a white, there's 10 balls, and we can pick from 7 whites. And then we go back in and we pick another ball. We want it to be white. There's only 9 balls remaining, and only 6 of them are white, because we picked the white for position 1. For position 3, there's only 6 whites remaining and only 9 balls remaining. Case 3 happens to go into both of these numbers 2 times and 3 times. 1 from the top, 1 from the bottom. And 2 goes into these 2 numbers, 1 from the top, 1 from the bottom. 1 time and 5 times. 7 times 1, 5 times 3. 7 out of 15 times, you will get 2 whites you get a white in the first and the third position 7 out of 15 times. A little bit less than 49%. Why is that? If I multiply this by 1 as 7 over 7, I get 49 over more than 100. Well, think about it. If you take your test and you got 49 points out of 105, if it was out of 100 instead, you would have had a little less than 49 points. We'll call it 49 minus, a little bit less. So yeah, it's less than 49%. So in this case, we did look at the reduced sample space. The reduced sample space were 7 whites and 3 blacks. Again, you can use the formula, but using the reduced sample space makes it much, much easier. Using the formula is quite awkward. If they gave me a Venn diagram, I would use the formula. Okay. here's an interesting set of problems. Okay. Your father comes from a family of 2 children. I'll assume your father is a male, a man. Man, woman. Okay, your father is a man. And your father has a sibling. Either it's another man or it's a woman. Boy or girl, if you prefer. So the question is, what is the probability that the other child is a sister? What is the probability that the other child is his sister? Okay, so you're given that. So, this is a family with 2 children. And you are given that one of them is a man. You are given that one of them is a man. You don't know if the man was the firstborn or the secondborn, but you guarantee there's a man. Well, you have 2 children. You can have male and then a female. You can have male and then a male. The firstborn can be a female and then a male. The firstborn can be a female, and the second one can be a female. But this one is out, because if there's 2 females in the family, where did this male father come from? So this here is our reduced sample space. 1, 2, 3. And they're all equally likely. That's important. So I know it's out of 3. Well, if that's the father, then his sibling is a sister. That's a favorable one. Let's look at number 3. If this is the father, then the sibling is the sister. And in condition 2, if that's the father, well then the other child is a male. That's not a sister. If you want to call this the father, well then his sibling is a man. Well, that's not a woman. That's not a sister. So, out of 3, 2 of them yield a sister as the second child. So it's 2 out of 3. Okay. Your father comes from a family of 2 children. Now I'm going to change it. Just one minor modification. Your father is their eldest, the oldest child. Your father is the eldest child. We'll have the oldest and then the youngest. Normally, you can have man and man, man and woman, woman or female, woman and a man, woman and woman. Well, these 2 cases get knocked out because the oldest child can't be a woman. So these are the only 2 cases. The first child is a woman. Well, in the first case, now we want to know that whether or not the older child is his sister. That is, a woman. Well, the other child can be the younger one. If you have just one of the siblings and you're the oldest child, well then your sibling is younger than you. Okay, so we have a man for the oldest or eldest, and then the youngest one is another man. Younger child, not a sister. You have the eldest being a man and the other one being a woman. That's yes. 1 out of 2. This time, it's 1 out of 2. So, knowing the order of the child, order meaning, firstborn or secondborn, it's going to change the probability. Without stating an order, the answer is the probability the other child is or sister is 2/3. If you do give an order, it's a half. Now you may say, well, you gave a particular order. You said the oldest child is the father. Well, what if we reverse it? You have the eldest and you have the youngest. Let's suppose the youngest is a man. So these are the same 4, and then I'm going to reduce it. The youngest is a man. That one's okay, that one's okay, because it's a man. But these 2 get knocked out, because that's a woman. The youngest is a woman. So we're only left with this one and this one. And you know what? If the youngest is a man, one time the other child is a man, and the other time the other child is a woman. 1/2. It's 1/2. So it doesn't matter if you told the youngest of my 2 kids is a boy, what's the probability the other one's a girl? It's 1/2. And if 50% of the time the other child is a girl, then the remaining 50% of the times the other child is a boy. We are going to assume either a boy or a girl. That's not up for negotiation in probability theory. Okay, so very similar problem and 2 drastically different answers. All right, suppose you flip a coin twice. Flip a coin twice. Okay, the first is our head. That's given. The first is the head. Given that the first is a head, find the probability that both are heads. Both are heads. Now, if you think about it, the probability of getting a head on the second toss has absolutely nothing to do with the outcomes of the first toss. You're not going to get a head on the second toss more or less likely than a half just because of what you got on the first toss of the die. Okay. So the answer, now to get both heads, you have to get a head and then a head. And we know we got the first head. That's given. So the answer is just going to be a half. But if you wanted to look at the reduced sample space, that's cool. You toss 2 coins, you can get a head, and then a head or a tail. Or a tail you can get first, and then a head or a tail. Well, these last 2 get knocked out because we are assured, we know that we got a head on the first toss. So the probability of getting head, given that the first toss is head, well, this will be, there are 2 equally likely outcomes, and only one has the second one being a head. So there it is. I think the easiest way of doing it is saying, you know what, this information is not helping me. It turns out that this is just equal to the second is a head. Knowing this doesn't give any information, okay? It didn't help us. going to talk about that in the next section or two. It didn't help us. Okay, so what I just did here, using the reduced sample space, that was the second easiest way of doing it. And now we're going to come back and we are going to use the formula. Okay, and as promised, this is going to be the hardest way of doing it. This is going to be the hardest way of doing this problem. The only time you do this one is either to practice using the formula or because you can't think of the easier way. So we want to know the probability of getting a head-head given that the first is head. That is, the given part is not saying what the second toss is. Head-head given either head-head or head-tail. We're just given that the first is the head. When I look at this, I say, oh, they got a head on the first. That's what I see. We are given that, oh, a head on the first. All right. So now, remember, or means union. So using the formula, this is the probability of getting HH, and it's this intersect this, and HH or HT, divided by the probability of this, getting HH or HT. Well, let's do the bottom. When you toss two coins, you can get head and then a head, or head and then a tail, or you can get a tail first and head or tail second. Out of four outcomes, out of these four outcomes, only this one or that one is HH or HT. So half the times the bottom will occur. Now what about the top? Now you need to remember that if you have A intersect B union C, this is A intersect B, or A intersect C. Well, H intersect HH, that's HH. HH intersect HT, that's union. That's the empty set. HH and HT, this one and this one. The intersection is empty set. They didn't have the same results. Union is empty set. Well, you add the empty set, you just get back HH. Anything, add on the empty set, union means add on, you just get the original set. What's the probability you get HH? 1 out of 4. I'm going to keep this as 4 in the bottom. Like it says on the left, it's 2 out of 4. So the probability of getting HH is 1 out of 4, and we divide this by 2 out of 4. The 4's cancel. I mean, just multiply both sides by 4. You'll see it. The 4's cancel. What survived is 1 divided by 2, a half. Same answer we've been getting all along. Much, much harder using the formula. Much, much harder using the formula. Let's try the next one. Okay. You have an urn. Let's try this urn. Let's see. In the urn, we're going to have 10 whites, we're going to have 5 yellow, and we're going to have 10 blacks. These are marbles. And for some reason, most of that didn't come out. You have an urn, 10 black marbles, 5 yellows, and 10 white marbles. A marble is chosen, and it is observed not to be black. So, you pick a marble, and it is given that it is not black. It is given not to be black. What is the probability it is yellow? If it is given that it is not black, then what is the probability that it is yellow? Okay. The probability that yellow, given that it is not black. Not black. Well, you're given that it's not black. There's no blacks. There are 15 marbles, and favorable or yellow. 5 are yellow. The answer is 1/3. You want to use the formula. It's going to be a nightmare, I suspect. This is the probability of this intersect that. The probability of yellow and not black, divided by the probability of not being black. Well, if you're yellow and you're not black, then you're yellow. Which of these marbles, including the 10 black, which of these 25 marbles are yellow and not black? Well, the whites are in yellow and not black because they're not yellow. The yellows are certainly yellow and not black. The blacks are not yellow and not black. Okay, the bottom we're not going to touch for now. The probability of being yellow. Well, there are 25 marbles in all, and 5 of them are yellow. The probability of not being black. Well, there are 25 marbles. These 15 are not black. The 25s cancel. You get 5 over 15, which is 1/3. Much, much more work doing this than the line above. Okay, so let's try the next one. A deck of cards is dealt to 4 players. There are 4 players. Let's spell it right. 4 players. 13 cards each. 52 cards in a deck. Divide them amongst 4 players. They each get 13 cards. Okay. It turns out that player 1 and player 2 have a total of, say, 8. A total of 8 spades together. One has 5 spades, the other has 3 spades. But player 1 and 2 have 8 spades amongst them. What is the probability that player number 3 has exactly 3 spades? Now, in my opinion, I think the only way to do this is to reduce sample space. These players, they've used up 26 cards. So, 26 cards remain. So I am removing their 26 cards and their 8 spades. There are 13 spades in a deck. The ace of spades, the 2 of spades, the 3 of spades, all the way to the king of spades. 26 cards remain. 8 spades remain. Now, player number 3 is to pick 13 cards. Player number 3 is going to pick 13 cards out of the 26. That's the total sample size. The number of ways of a 13 card hand that player number 3 is going to get. Now, player number 3 is going to have 2 categories of cards. They're going to get spades. They're not going to get spades. Of the 8 remaining spades, you want player number 3 to get 3 spades. You want player number 3, oh no, excuse me. There are 8 spades between player 1 and 2, so there are 5 spades remaining. Okay, there are 5 spades remaining. There are 5 spades remaining, and from the 5 spades, you want player number 3 to get 3 spades. There are 26 cards remaining. 5 are spades, 21 are not spades. Player number 3, just like every other player, is going to get 13 cards. So from the 21, player number 3 is going to get 10 more cards. They've already taken 3, and now they are going to be given 10 more. This is the probability that player number 3 will get exactly 3 spades from the remaining 5, if they're going to get 13 cards. Okay, let's try this. But first, I need to give you a definition. Okay, this is called, if I remember correctly, this is called the multiplication rule. Suppose you have many events, and they don't have to be increasing or decreasing. The probability of E1 intersect E2, etc., all the way up to intersect En, well, this is nothing more than the probability of E1 given the ones before E1. Well, there is nothing before E1, so I can just close it up. Times the probability of E2, E sub 2, given the intersections of the ones before. Before E2 is just E1. E1, E2, now E3. The probability of E3, given the ones before. Before E3 is E1 and E2. Intersect them. Times. I'll continue down here. The probability of E4, given the intersections of the ones before. Before E4 are E1, E2, and E3. The intersections of those. Dot, 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 up to En. The probability of E sub n, given the ones before that. E1 intersect E2, all the way up to, well, the one before En is E sub n minus 1. And you can easily prove this because, well, let's just work with this. This is equal to P of E1, this one, times this, which is P of E sub 2 over P of E1. And that cancels. Times this. That's the probability of E sub 3. divided by the probability of E1 intersect E2. Okay, so let me state that right. Now I see why I didn't feel good with that. This probability is the probability of this intersect that, which is E1 intersect E2 intersect E3, divided by the probability of this, E1 intersect E2. And when I went to do this one, the numerator should be probability of E1 intersect E2. I should have in here E1 intersect E2 or E2 intersect E1, but nonetheless, this cancels. If you notice, what survives is just P of E1 intersect E2 intersect E3. And I'm not going to really continue with this, but if I did, I would just get probability of E1 intersect E2 intersect En. Okay, it does work. Get your hands dirty, work it out. Okay, that's the multiplication rule. So, harder rule gets followed by a harder problem. Okay, an ordinary deck of 52 cards is again divided into 4 piles. So you take the deck, you divide them into 4 equal piles, meaning each pile 13 cards. And we want to know what's the probability that exactly one ace is in each pile. Pile 1 has one of the aces, pile 2 a second, pile 3 third. The last ace goes in pile 4. We want to know what's the probability that that happens. Just cut the deck into 4 equal parts. What's the chances that each pile has one ace? Okay, so how about we define E1 to be, I don't know, the ace of clubs is in one pile. And E2 is the ace of clubs and the ace of diamonds are in different piles. And E sub 3 will be the ace of clubs, the ace of diamonds, and the ace of spades are in different piles. And E sub 4 is, I guess, all aces are in different piles. These are sets. Now, if you think about it, if all aces are in different piles, then the ace of clubs, ace of diamonds, and ace of spades are in different piles. And the ace of clubs and the ace of diamonds are in different piles. And the ace of club is in a pile. So the probability that all aces are in different piles, and that's what the question is. What's the probability that one ace is in each of the piles? That is, all the 4 aces are in different piles. Well, that is the probability of E4. But E4 turns out to be E4 intersect E3 intersect E2 intersect E1. And I prefer to write it in this order. That is, this is equal to the probability of E1 times the probability of E2 given E1 times the probability of E3 given E1, so let me write the given then formula. Given E1 and E2 times the probability of E4 given E1 intersect E2 intersect E3. Okay, so let me erase a lot of this and we'll start getting this all together. It's not a very hard problem once you made these 4 definitions. The probability of E1, the probability that the ace of clubs is in one pile is guaranteed. It's in the 52 cards. Divided into 4 piles, it's going to be in one of them. The probability of E2 given E1. Okay. Well, E1 talks about the ace of clubs being somewhere. And E sub 2 talks about the ace of clubs and the ace of diamonds not being in the same place. Okay, so we placed the ace of clubs. Maybe we put it in pile number 2. There are now 51 cards left over, and we can put them in any one of the remaining 39 positions. 13, 13, 13. The probability of E3, so we're going to do this one now, given E1 and E2. Well, E1 and E2, actually this happens to be, I don't know if it's increasing or decreasing, but E1 talks about the ace of clubs, and E2 talks about the ace of clubs and the ace of diamonds. This one I had to write down. Okay, so the intersection of these two, say E1 is in one pile and, ace of club is in one pile, and the ace of club and the ace of diamonds are in different piles. So we've used 2 piles. We've used 2 piles. Maybe the ace of club is here and the ace of diamonds are here. There are 26 slots, first and fourth, for their E3, which includes the ace of clubs, the ace of diamonds, the ace of spades. Now, there are 50 cards remaining. There are now 50 cards remaining. The probability of E4 given E1, E2, E3, well, E1, E2, E3, E1 is the ace of clubs, E2 ace of clubs, ace of diamonds, ace of clubs, ace of diamonds, and the ace of spades. The intersection will be all these 3 are in different ones. Say 2, 3, and 4. So there's only one place to put that remaining ace. And that's one of the 13 cards in pile 1. And there are 49 cards left over. And the probability that all aces are in different piles is the probability of these 4. But we just did that. The first one was 1 times the second one, 39 over 51, times this one, 26 out of 50, times this last one. Okay, multiply these out, get what you get. Okay, this finishes the section on conditional probability.